Welcome back. We're almost there, almost there. This is, let's see, one of 3 lessons left for the week. We're going to transition into functions for these last couple of days. And it's still exponential, but the exponential equations, right, just had one variable to solve for. Now we're going to put 2 variables in the equation and then try to graph the relationship between those 2 variables. So, exponential functions are in the form y equals b to the x power. So that's sort of like the parent function in this situation. But there are some stipulations for this function, in particular for b. So remember, exponential equations were exponential not because they had an exponent, but because the variable was the exponent. That's still going to be true here. What makes a function exponential is the fact that the exponent is a variable. The exponent is a variable, or the variable is an exponent, either way, whatever. But there are some stipulations to the base of that exponent. So in particular, the base in this exponent b, oh, I'm like, why did I put such a small blank? Now I remember. Okay, where b, the stipulations, b can't be 0, for instance, because if we take 0 and raise it to any power, we're going to get 0 every time, and that would be a constant function. That's not what we're looking for here. And the same happens if our base is 1, right? 1 to any power is going to be 1, so we'd get a constant function there too, not an exponential. So to see the exponential relationship, b can't be 0, b can't be 1. Can't have a base of 0 or 1, but any other real number is going to be fine. So b can't be 0, b can't be 1, and the exponent can be any real number. All right, again, the exponent being the variable is what makes this exponential. Now, I know we have technology that graphs for us, but I really want you to have at least a basic understanding of what's going on with the exponential function, and I don't think we talked about these with the parent functions at the start of the semester. So we're going to graph the old-fashioned way. We can graph any function making a table, and that's the approach we're going to take here. And we're going to start with a base of 2. So what happens when I plug in a negative 2? If I have 2 when I raise it to the negative second, hopefully we remember, let's say you forgot and you put it in your calculator. 2 raised to the negative 2 power is a 1/4. That's because our negative exponent rule says if we have anything with a negative exponent, we move it to the other side of the fraction to make the exponent positive. So 2 to the negative 2 is really 1 over 2 to the positive 2, which is why the calculator said 1/4. So this is 1/4. So then if I make this a negative 1, 2 to the negative first would be 1 over 2 to the positive first, which would make it a half. How about 2 to the 0? Anything to the power of 0, if you forget, right, you use your calculator, but 2 raised to the power of 0, anything raised to the power of 0 is just going to be 1. So 2 to the power of, I'm going crazy here. Come on, eraser. 2 to the power of 0 is 1. 2 to the first, we don't need a calculator for that. 2 to the first power is just going to be 2. And then 2 squared is going to be 4. All right, so let's try to make this picture. If I go here, let's see, negative 2, we have a point at a 4th, maybe up here-ish. Negative 1, we're up a little higher to a half. 0, we go up to 1. 1, we go up to 2, and then 2, we go up to 4. So this is the little piece we have of our graph that's coming from our table, but obviously that won't be everything. So what's going to happen is we continue to pick bigger values of x. So if we put a 3 in there, 2 cubed is 8. Put a 4 in there, 2 to the 4th is 16. Put a 5 in there, 2 to the 5th is 32. Right? If this number, we can see it's multiplying by that base of 2, right? We're just doubling every time. It's going to start to grow really fast. So as we go this direction, right, we said 2 cubed was going to be 4, 5, 6, 7, 8. Right, this direction, this graph is just going to continue to grow really quickly. So this is 2 to the x power here. Okay, now what happens the other direction? As I keep picking smaller values of x. So when I put in a negative 2, I got 1/4. It was 1 over 2 squared. If I put in a negative 3, I'm going to get 1/8. Put in a negative 4, I'm going to get 1/16. Now, as small of a number as I want to pick, it's just going to make the bottom of the fraction bigger, which means the value of the fraction is going to get smaller. Now, how small is it going to get? it's going to get infinitely small. So on this side of the graph, we're going to be getting closer and closer to the x-axis, but we won't be able to get there. So there's going to be an asymptote in that graph, similar to what we saw with our rational functions. Okay, now let's change this to a base of 3. What's happening with the base of 3? Well, 3 to the negative 2 is 1 over 3 to the positive 2, which means it's 1/9. And then if I had a 1 here, then it'd be a 3 here, so 1/3. Anything to the power of 0 is 1. 3 to the first is 3, and then 3 squared makes 9 here. So this first half of the graph, I don't know if we're really even going to be able to distinguish. Negative 2, I'm at a 9th, and then I'm at a 3rd, and then I'm at the same point here of 1. But then at 1, I go up to 3, and at 2, I go all the way up to 4, 8, 9. And so this side of the graph, again, is going to look pretty similar. But on this side of the graph, what happens is the graph is steeper. And again, the same thing will happen if I continue to pick bigger values of x, we get bigger, faster, and then smaller values of x, we get smaller, right? Now, why is this graph steeper? Well, look at what's happening here. Instead of over here where we're multiplying by 2, and then we said put in a 3 to get 8, multiply by 2 because there's a base of 2. What's happening on this one is we're multiplying by 3. And when we multiply by 3, the number grows even faster, so it gets steeper. So you can imagine if I had like a 10 to the x or a 12 to the x, the bigger that base gets, the steeper or faster that graph is going to climb, okay? Now what happens if I put a 1/2 in there instead of a 2 over 1, a 1 over 2? So if I have 1 over, let me change colors here, 1 over 2, and I raise it to the negative second. Remember, the negative exponent says move stuff to the other side of the fraction. So the 2 goes to the top, the 1 goes to the bottom, and then I can make this a positive 2. So negative 2, or 1/2 to the negative 2 is really 2 squared, which makes it 4. If I made this a negative 1, I still flip the fraction, make it a positive 1, so then I get 2 here. And then anything to the power of 0 is 1. 1/2 to the first is itself. 1/2 squared is going to be 1/4. So if we plot these points, what's happening? So at negative 2, my graph is up to 4. Negative 1, I'm at 2. 1, 1 again. And then I'm at a 1/2, and then I'm at a 1/4. So comparing these two, what's happening? Well, instead of my graph growing really fast, instead of multiplying by 2, now we're dividing by 2, and this graph is shrinking. So we have a graph that is going to be decreasing. And again, this side is going to continue to grow really fast. This is 1/2 to the x power. And then we probably know what's going to happen with this next one here, but just in case. If I put in a negative 2, this is going to give me 3 over 1 to the positive 2, so 3 squared makes 9. This is going to be 3. Anything to the 0 is 1. This will be a 1/3, and this will be a 9th. And so we have at negative 2 up to 9. And here, same-ish. So this graph is going to be our 1/3 to the x power. Okay, so you can kind of see some similarities and differences here. Let's make some generalizations, right? These are graphs of exponential functions. What's going to happen every time we graph an exponential function is you're going to get a picture that looks kind of like one of those. Just like every time you graph a parabola, you know that it can shift around or be stretched or compressed, but it makes a parabola, right? Every time you graph a quadratic function, it's a parabola. So same concept here. Every time you graph an exponential, you're going to have that sort of shape happening where your number is going to start to grow really fast, or it's going to start to decay really fast, okay? Now, there are some things in common to all 4 of these graphs, and that is our domain. So remember, domain is x values, right? What the heck? Paper's going bananas. X values. What x values are possible for these functions, or how far left and how far right do these graphs go? Well, we see them go left and right forever because there's no restriction on what I can plug in for x. I can raise 2 or 3 or any number to any power and it will produce an answer. So every exponential function, just like a quadratic function, goes left and right forever. So every one of these exponentials will have an infinite domain, a domain that is all real numbers or everything from negative infinity to positive infinity. Now, is that true for the range? Are all y values possible? Well, no, we said, in fact, go away, we said that, in fact, these fractions would get smaller and smaller, but that we couldn't even get to the x-axis. So there was an asymptote in the graph. So the lowest y value we're approaching is 0. We can't be anything negative. And that's why we saw in our exponential equations or in our logarithms that those bases couldn't, that our answers couldn't be negative, or we couldn't take logs of negatives, because we just can't get there. No matter what we raise a number to, no matter what power we put in there, we can't make the number negative. We can't even get it to 0, let alone a negative. Okay, so these ranges are restricted, and in these cases we are going from, don't want a highlighter anymore, we're going from 0 and then up forever toward positive infinity, and we can't get to 0, so we're going to keep a parenthesis on it to exclude that. And since we couldn't get to 0, there was no x-intercept for any of these graphs, no x-intercept, and every single one of them had the same y-intercept. They all crossed the y-axis at 1 because anything to the power of 0 was 1. Every time we put a 0 in for x, we got 1 back for y. So the y-intercept was always at 0, 1. And there was a horizontal asymptote happening at the x-axis. So horizontal asymptote at, or barrier at x equals 0. Just kidding. At y equals 0, which is our x-axis. Okay, and then the only real distinction, so far these all four of these graphs have those things in common, but there was a distinction, right? The first two graphs we saw the numbers grow, and the other two graphs we saw them get smaller. So we were like doubling or tripling, and then we were dividing by 2 and dividing by 3. So when the base was bigger than 1, that's what happened in the red and the blue. When our base is bigger than 1, remember it can't be 1, but if it's anything bigger than 1, we're going to get growth, because that base is the factor that we're going to multiply by every time we continue. So if that base is bigger than 1, let's say it's 2, we're doubling. Let's say it's 3, we're tripling. Let's say it's 4, we're quadrupling our number. When that base is bigger than 1, the graph was increasing. And so we call those types of exponential functions exponential growth. We see the numbers grow really fast. And then when that base is some fraction between 0 and 1, anything between 0 and 1, like the 1/2, we saw the numbers get half as big. The 1/3, we saw the numbers get a third as big. If you're dividing your number down, right, if you're cutting it in half or cutting it by a third, then your graph was decreasing. And those that decrease in that fashion we call exponential decay. Okay, so that's sort of the basics for exponentials, but again, we know the transformation rules can apply. Now, if you have just a basic here with nothing being added or subtracted or multiplied, we don't put any negatives in there, we don't have any transformations applying, then these characteristics will be true. Now, if I shift everything up 1, or if I shift down 2, or if I reflect, then obviously some of these characteristics will change, okay? So the transformation rules, they still apply. Our standard form is a times b to the x minus h power plus k, and hopefully we remember that a affects the width of the graph. It will also tell us if we have a reflection. H tells us if the graph is going to move left or right, and then k tells us if the graph is going to go up or down. So let's say we're comparing to y equals 2 to the x power. If I'm looking at y equals 2 to the x plus 3 minus 1 power, well, that plus 3, hopefully we remember these, that plus 3 makes our graph go to the, do you remember? Plus 3 makes it go to the left 3. And then this minus 1 is going to make our graph go down 1. Now, let's say you forgot. Remember, we do have technology that graphs for us, okay? So let me fix my graph here. If we're comparing 2 to the x power, and we want to know what happens with just the plus 3. Let's put in 2 to the x, let's put a plus 3 in there, and we can see what happens. Everything has slid over to the left, okay? And then let me take that plus 3 out of there, 2 to the x power after the exponent, and if I subtract 1, we can see that that graph has shifted down, okay? So if you forget your transformations, you could use your calculator. your Desmos. All right, here we got a bunch of things going on. So we got a negative out in front. That negative is technically going to reflect the graph over, reflects over the x-axis. The 1/3 is a compression of the graph, vertical compression of the graph. That should make sense, right? In this case, you're doubling, but now you're going to cut that by 1/3, so it's going to shrink it down a little bit. So this is a vertical compression by a factor of 1/3. And then we have a -2 here, which makes our graph go to the right 2. Okay? And one more. So this time we have a vertical stretch of the graph. I lost my word for a second. A vertical stretch by a factor of 3. This negative is going to make the graph reflect over the y-axis. And then this +4 makes the graph go up 4. And I just want to go back to that reflection over the y-axis. So we have a negative in there in the exponent. And what does the negative exponent do? Okay, if I had 2 to the x power versus 2 to the negative x power, we said on the front there that the negative exponent meant we had to take that base, move it to the bottom of the fraction to make the exponent positive. So this is really equivalent to 1/2 to the positive x. And that's why we saw the 2 to the x power that did this. And then we saw the 1/2 to the x power was a reflection over the y-axis. It changed the direction there. Now it was decreasing because we were cutting that in half, but that negative flips that fraction, and we can see it's the same concept. It reflects that graph over the y-axis. Okay? Now, the base of e. Now, we mentioned e before. It came up when I first introduced natural logarithms to you, and it was a brief mention. But the reason it's significant, and we'll see applications of it in the next lesson. But e, we call it, how would you say this? Like, when I first read this, I was like, Euler? Because that's what it looks like. Technically, it's pronounced Euler. Euler's number, e, because a man named Leonard Euler discovered it, but it's, if you recall, an irrational number. An irrational number meaning it's a non-repeating, non-terminating decimal like pi, right? 3.14159 that goes on forever. Except e is approximately 2.7182. Again, goes on forever. We say it's about 2.72. And again, often used as the base of an exponential function, particularly when you're looking at finance. And again, we're going to see some applications of that. But e, like any other number, could be the base of an exponent. So e to the x, I just want you to see it here. We should really already know what this graph is going to look like, because if e is 2.72-ish, what would our graph look like if it was 2.72 to the x power? Well, since this base is bigger than 1, we're going to see a graph that grows, okay? So it should look very similar to the first two that we graphed from the front. But let's go ahead and make a table. Let's see, e to the -2nd. If I put in e and I raised it to the -2nd power, I'm going to get about point. Now, how much decimal should you keep? I don't know if you're going to be able to distinguish between 0.1 and 0.14 when you make this graph by hand. So I'm just going to say about 0.1 here. And let me change that to a -1. Then I have about 0.4 here. Anything to the power of 0 is 1. E to the first, we shouldn't need the calculator for. We said it's going to be about 2.72. And if we square it, we're going to get about 7.4. So what we're going to see, again, looks just like what we saw in the front. -2, we're down here. -1, we're up a little higher. 0, we're at 1. 1, we're at 2.7. And then 2, we're up to 3, 6, 7.4-ish. Right, there we have it. And as this exponent gets bigger, so will this graph. And as the exponent gets smaller, we're going to get closer and closer to the x-axis. So what we have is an increasing graph, exponential growth, right? It's growing because that base is bigger than 1. We have an infinite domain, and we have a range that goes from 0 to infinity. No x-intercept, y-intercept at 1, asymptote at the x-axis, which is where y is equal to 0. And then end behaviors. It's been a little while since we've seen these. As x goes to infinity, means if we're on the x-axis going toward infinity, we're looking to the right. If I go to the right end of this graph here, where are these y values headed? They are headed up toward positive infinity. So this end of the graph goes toward positive infinity. Now the other end, let's be careful. This goes up to positive infinity. The other end, as x goes to negative infinity, that means go to the left end of the graph. If we go to the left end of the graph, where are the y values headed? Well, you might be tempted to say negative infinity, but the y values, right, they're going to be stuck with this asymptote. These y values, and we saw this in the table, these y values here, they're going to get smaller and smaller and smaller. They're going to get closer and closer to 0 is what they are approaching. Okay, these y values get closer and closer to 0. They can't go past 0 because there's a barrier there. Okay, and then the transformation rules, A, H, and K, they still apply. So if I put like a +2, I can make the graph go up 2. If I put a 2 out in front, I can make the graph grow faster. It'd be a stretch. Same rules apply. Okay, so just wanted to reinforce that E is just another number, but it's often the base of an exponential function. All right, let's graph one more just to make sure we're all good. And remember, we do have technology. Remember that Desmos could be used, your calculator could be used to confirm what you're doing. So transformations, let's see. First, the parent function in this one is just 5 to the x. Well, if I stick a negative out in front there, it's going to be reflected over the x-axis. Reflected over the x-axis. If I put a -1 in the exponent, the graph is going to go to the right one. And if I put a -2 after the exponent, the graph is going to go down 2. And remember, the purpose of those is to be able to try to make a sketch. So if we were trying to sketch this, 5 to the x would look like this, right? Or it crosses at 1. If I reflected that over the x-axis, then it's going to go here. And then if I took that and shifted it to the right 1 and down 2, this would be the easiest point to move right 1 and down 2. If I want right 1 and down 2, it's going to be basically shifted a little, but it's hard to discern what that would look like, right? So let's go ahead and go to Desmos and try to make a nice picture here. Alright, so delete all this. Let's see, we're looking at y equals -5 raised to the x minus 1 power, and you're going to have to put parentheses in the exponent there, or otherwise it won't keep those two terms together. And then we are subtracting 2. Okay, so there's our picture. Now, where is our asymptote? We're going to draw that in. You can kind of see it, right? It looks like these values are getting closer and closer to -2. Does that make sense? Well, if the original asymptote was at 0 and this graph shifts down 2, it should make sense that the asymptote has shifted there. So I'm going to put the asymptote in there at -2, so I know my graph can't get there. And just so I can make a halfway decent picture, it's crossing the x-axis at the y-axis at -2.2. So like around here-ish. It's going to get closer to the axis that way, and then it's just going to grow as we go this way. Okay, so something like that. Alright, so increasing or decreasing? Well, if we read this graph from left to right, it's definitely decreasing. Now we have to be really careful here. Just because this graph is decreasing does not mean that it is decay, because the base of our exponent is this +5. That is exponential growth. It's because it reflected over the x-axis, because there's a transformation there, that it's decreasing. But this is technically exponential growth. It's just growing in the negative direction. So even though it's decreasing, this is still growth, because the base, b, is 5, and that's bigger than 1. So because it reflected, it's growing in the negative direction. We call it negative growth. It's ridiculous, right? All right, domain. We could still plug whatever we wanted for x. The graph still goes left and right forever. The range. Well, now the graph goes down forever toward -infinity, and then it's going to be approaching 2. It's going to be approaching the asymptote at 2, but it can't quite get there. X-intercept, still not going to cross the x-axis, so none. The y-intercept we found from Desmos was at, I forgot, -2.2, so 0 and -2.2. And if you want to make a little note, that came from Desmos. And then the asymptote, we sketched that in, and again, this should have made sense. Instead of being at 0, like it was with the parent function, the whole graph shifted down too, so did the asymptote. Shifted down to y equals -2. So as, I don't know what happened to x, as x, I don't know what happened to x. There should be an x in here. As x goes to infinity and as x goes to -infinity, if we follow the right end of this graph, the right end of the graph, the y values are going down forever. So these go toward -infinity. And then if we follow the left end of the graph, these y values are getting stuck, right? They're going to get closer and closer to that asymptote at +2, or -2. Okay? Now, just to recap, most of that graphing and reading of graphs we can handle. You should be able to look at a function, whether it's the graph or the equation of the function, and determine if we're looking at exponential growth, if we're looking at exponential decay, or if we have something that isn't exponential. So if we look at the first picture, does it look like one of those graphs that we made? Does it have the characteristics where we're growing or decaying and we have that horizontal asymptote? Yeah, this does. And in fact, this one is exponential growth. We see those values getting bigger. How about the second graph there? Nope, no asymptote in that graph, no horizontal asymptote in that graph, tells me there's no restriction. This is probably a polynomial function, likely a degree of 3. So this is neither. It's not exponential. Okay, and then this last one we can see is definitely exponential decay. Exponential decay. It looks like those second ones that we put up there. Okay, now what about the equation? If it's, first we have to determine if it's exponential, right? If it's exponential, that means the variable is an exponent. First graph here, this exponent, not a variable, or the variable, not an exponent. Either way you want to read that, I can tell that this is neither exponential growth or decay. That is a cubic function. This is a variable exponent, this is a variable exponent, this is a variable exponent. This is not a variable exponent. That is a linear function, so that is neither. And then the last one has a variable exponent. So we've eliminated the two that are not exponential. Now, which ones are growth, which ones are decay? Remember, for growth, the base has to be bigger than 1. And the base of this exponent, not bigger than 1. The base of this exponent, not bigger than 1. This is bigger than 1. That is growth. That was a neither, and this base, bigger than 1, is growth. When the base is between 0 and 1, like 0.75, it's decay. Between 0 and 1, like a third, it's decay. And that's it. Got them all. Okay? So the base is going to tell you if we're multiplying